Let's imagine the famous Schrödinger cat experiment. We put a cat and a bottle of poison in a box, together with a radioactively decaying material. If an atom of this material emits an electron, a little hammer will break the bottle and the cat will die. So before we open the box, we cannot observe the state of the cat. So until then, the cat is in some superposition of being alive and dead. This means that the fate of the cat is in the hands of the quantum state of the atom. What is the probability that the cat is still alive or dead after we open the box? The Born rule tells us the answer to this question. This fundamental law in the theory of quantum computers tells us how likely the possible outcomes are when we measure a qubit. After this video, you'll be able to predict quantum measurements with just a simple mathematical trick. Remember that we can write down any qubit state as a superposition of the 0 and 1 state. So psi is alpha cat 0 plus beta cat 1, where alpha and beta are two complex numbers. The Born rule states that if we measure the state psi, the probability to find the qubit in the 0 state is the absolute value of alpha squared. And likewise, the probability to measure 1 is the absolute value of beta squared. Now there is a strict condition on the coefficients alpha and beta. The total probability of the measurement outcomes should always add up to 1. Or the absolute value of alpha squared plus the absolute value of beta squared must equal 1. Now let's go back to our Schrödinger cat experiment, where we can associate the 1 state with the cat being alive and the 0 state with the cat being dead. Suppose your quantum state can be written down as follows. So psi is I over square root of 3 times cat 0, or dead cat, plus square root of 2/3 times 1, or alive cat. Now the probability to find your cat dead is the absolute value of I over square root of 3 squared, and this equals 1/3. Then the probability to find your cat alive is this absolute value squared of the square root of 2/3, which equals 2/3. You can see that this state obeys the condition on the coefficients alpha and beta. If we sum up both probabilities, 1/3 and 2/3, we obtain 1. A state that obeys this total probability condition is also called normalized. If you want to apply Born's rule to predict the measurement probabilities of a state, then make sure the state is properly normalized.